lofting material into the air and letting it go on a course through interplanetary space, or as you've mentioned in this other paper, through more recent bombardment by dust in the upper atmosphere. It's seemingly counterintuitive, actually, when we consider this. It sounds kind of crazy, until you stop and realize that planetary formation is a very dynamic process. The early solar system, early epoch of planetary formation, you had planetesimals that were dynamically interacting both with each other and with their nascent disk. So it was a very violent and dynamic process. And that gas and dust clears out rather rapidly, but even today we have this remnant material. So you go through the calculations and you say, yes, it's possible, but I guess I would ask, is it necessary? I agree with Gary's viewpoint that it kind of violates an Occam's razor, if you will. I don't think it's necessary. Moreover, in the solar system, the process takes hundreds of thousands of years. So it's very slow. It's not very efficient. I find this technique much more intriguing on some of these other planetary systems that we found, like the TRAPPIST system, where you have 7 planets packed dynamically into an area that fits within, let's say, Mercury's orbit. So there, the transfer process is like decades, 100 years, not 100,000 years. So I think in systems like that, it's much more compelling.
Can you help me to visualize, so let's say there is asteroid coming in the atmosphere, obviously it's very hot, temperature is very high, and let's say there's some bacteria traveling there. So are they going to survive this last phase?
Well, that's the question, whether you're talking about a collision, which is very violent. So an organism, and we can think about either life, actual microbes, or maybe just organics. If we can take these complex molecules and allow them to survive these violent processes so that they can then seed life someplace else.
How they will survive?
Well, it's challenging. They're going to have to burrow themselves into the lithosphere of an object. They're going to have to survive.
A little bit underground, right?
Yes, that's right. And during their interplanetary voyage, they probably also have to be buried within the rock and then released rather gently as they collide back on the other planetary surface. So, the odds of that happening are small. It's difficult, but calculations say that it's possible. I'm convinced that it's possible, and that these events happen frequently enough during the formation stages and even later stages of the solar system's life that it's possible, but hard.
So, Gary, do you agree that you kind of need to sit inside this rock and hide there for a while and then survive the landing?
I mean, an asteroid smallish, a few meters across coming towards Earth, 80 degrees Kelvin, enters the Earth's atmosphere. Yes, it gets very hot where at the crust smalls off in the center. It's still 80 degrees Kelvin, right? Now, when it collides, there's a lot of energy released, but there's shock waves where there isn't heating. Geologists have done lots of calculations, even experiments on this. So transfer of life by meteoritic exchange, it's hard, but it's not impossible. The other thing to keep in mind is that this revolution in exoplanets that you've been so involved with has been magnificent. It has all these hot Jupiters that are spewing planets like crazy. So movement between star systems can be entire planets. It doesn't have to be pieces of rock. If Earth got ejected tomorrow, we wouldn't do too well, but the bacteria on Earth would do just fine, thank you very much. And for a billion years to sort of hang out, they could do that.
Meaning that the Earth could be older than 5 billion years. In that case, the Earth would be older than 5 billion years.
Well, I'm not saying Earth was captured, but it's something analogous to Earth. Could see
something like that.
Yeah, it could go to the next planetary system. And every star has an orbit belt around it probably, and those orbit belts are very loosely coupled and it's changing like crazy as the stars sort of sweep next to each other.
Lyman, to sort of put some boundaries on how early in the life of the universe life could have emerged. We know that the universe is roughly 15 billion years old, 14 billion years old, rather.
13.8.
So at what period of time we can assume that now life can emerge from what we know?
So something like that happened. The first stars have to form to make these elements of life. So something like 1 billion years, the process could start. And yes, we heard about earlier, early on is also a great time because you don't have to travel these great distances. Things are closer together and moving around a little more. So they could well start then and end up here, whatever, 13.8 minus 1 minus 4.5 billion.
So basically now universe life had about 13 billion years to develop.
Yeah.
So Gary, just one thing to add to keep in mind is the one thing that panspermia offers you is the ability to use what you know to look for life. Without panspermia, you'd say, well, maybe there should be genetic storage. And genetic storage could be anything. But with panspermia, you say, let's look for DNA. And we have a $1 trillion industry that's really good at looking for DNA. So isn't it stupid to not look for DNA? Because we have such a great sensitive ability to do it. We can find criminals with their DNA.
Now, again, assuming panspermia is the way to go, which you've been convincingly arguing, do you believe it's more likely that life here could have come from the other star system, like with this object which is now moving across the solar system that we all read about in the last few weeks, or you think it's more likely that it came from another planet orbiting the sun, like Mars? I mean, you're doing Mars sequencing.
The only place you can go, or some of the outer planet moons, you're not going to go to, or you want to go to Alpha Centauri. I can't imagine going to Alpha Centauri to look for life, but you can go to the nearest planet to look for it. So exchange between Earth and Mars is sort of the most narrow view of panspermia. It's sort of bispermia, and so it's not nearly as it doesn't bother you all that much because it's pretty much anthropocentric, right? If you're privileging Mars, you're not much different than privileging Earth. So personally, I'd rather it came from somewhere across the Milky Way. I wouldn't posit it coming from Andromeda.
I feel like Gary needs some balance here.
Yes.
So what you're saying is that the exchange between galaxies is basically right. So it has to be within one.
I can't imagine it, but early on.
But why is it necessary? I mean, the building blocks of life are everywhere, right? We look out into the interstellar medium, and there's already the seeds of complexity. We see them everywhere in the solar system.
in pretty much all the galaxies something should be going on. And in fact, there was this astronomer, Jason Wright, who did these sort of galaxies looking for signs of civilization. So his assumption was that those Dyson spheres would be visible in infrared spectrum, and if there are enough of those spheres in the galaxy, then there will be some additional radiation coming in from infrared. So he looked at those, at a number of galaxies, and didn't find any sizable anomalies. So Lyman, what do you think about that type of experiment?
As I say, just backing up, galaxies do interact, right? We see it all the time. We see trails from galaxies, smaller galaxies passing through ours. I think there can be transfer there. But these, yeah, what are the limits? So I heard about this, and I think ultimately the limit, and I don't know much about Dyson spheres, but it seems like getting rid of the energy. I don't see any limit to making energy. It's how you get rid of it and survive. And so this is how it makes complete sense to me. That's how you look for it, right? Is to look at this infrared emission, and that you don't see it or put some limit on it. That's the size of how big another civilization could be. So that makes sense.
But and civilizations have gigantic planetary scale energy sort of harnessing.
Yeah.
Mercury don't do that.
Well, I mean, the idea is to look at the craziest things we can imagine first, right? Because they're the easiest things. I mean, we have this Kardashev scale that was hypothesized that, we need energy. Complexity needs energy, and technology needs energy. So the idea that on a planet, maybe we will evolve to the point where humans can make use of all of the incident radiation from our star, the sun. And imagine taking that a step further and saying, well, maybe one day we'll be so complex and evolved, we will need energy, we will need to harness energy from the entire sun. And then Jason Wright took it further and said, well, maybe you can keep growing that complexity and evolution exponentially, and maybe you get to the point where you would want to harness the energy of an entire galaxy, or you would have life capable of harnessing the energy of an entire galaxy. And it sounds crazy, but it's worth looking, right? Let's go out and look at the galaxies. We certainly have surveys that have done that, and the WISE survey was one that did that. And look at the galaxies and see if you see anything weird. Are there any galaxies out there where there's anomalously low optical radiation emanating from stars, but a mysteriously high infrared radiation that's in the form of waste heat? So he did this study, and again, it might seem crazy, but it behooves us to go out and look. And as you might expect, he didn't find anything unusual. Okay, but so what, right? It doesn't mean that life isn't out there in abundance. It just means that these galaxies, or these civilizations that maybe have learned to harness energy from the entire galaxy are not common.
So any other signs of sort of stellar or galactic civilizations we should be looking for?
Logical SETI. Heard about this afternoon, right? Something we should be looking.
But looking for atmospheres on exoplanets is asking for sort of material life, like what happened here with the production of oxygen. That's very promising.
Yeah, there's different pathways for looking for life. I mean, the one that I'm most tied to is the search for biosignatures. So looking for a global biosphere. That is a planet that has really become where life has transformed it into a living world so that you could see the global effect of life on the atmosphere. That's one pathway. And then you've got the SETI pathways, which also kind of bifurcate. You've got SETI searches that are involved with communication, trying to hear technological signals. I think that's what most people are aware of when they think of SETI. But there's also this idea of artifact SETI, where you look for these kinds of structures. So maybe life trying to harness energy from a star. And Kepler actually found a star called Tabby star that maybe...
And then you imagine adding all 6 consecutive numbers, then I think you would get 6a plus 15. And it might not be completely obvious what that kind of number is. So there are two things about that. One is that it tells you it must be an odd number, because all multiples of 6 are even. So if you add an odd number, you may get an odd total. But of course, it's not every odd number. So one thing you can do here is say, well, look, I know that's a multiple of 6, and if I add another 6, I will get another multiple of 6. Can I add another 6? Yeah, I've got 15, so I'm all right. So I've got 6a plus 6 plus 6 plus 3. So I can split the 15 up into groups of 6, something left over. And then I can say to myself, all that there is a multiple of 6. And then I've got to add 3. So that was very similar to the multiples of 4, where we had a multiple of 4 plus 2. For 6 consecutive numbers, we get the multiples of 6 plus 3. Okay. Somebody came up to me and said that you thought that powers of 2, so 1, 2, 4, 8, 16, 32, 64, cannot be written as sum of consecutive numbers. Now this seems quite difficult to prove, because these go on forever. There are an infinite number of these. And how are we going to prove that this can't ever be done with either 2 or 3 or 4 or 5 or 17 consecutive numbers or 162 consecutive numbers? It seems like a really difficult thing to prove. So let's think about, first of all, what's special about these numbers as compared to sort of all other numbers. If I take a number like 16, say, all the factors of 16 are even. So 16 is made up. And they're even because if I express 16 as a product of its prime factors, then that's 2 times 2. So there are no odd factors. that contribute to building up 16. Whereas with all the numbers, you get at least one odd factor. So if we take 30, for example, 30 is made up from 2 times 15, and 15 is 3 times 5. So it's got some odd factors. If I take 40, that's 2 times 2, times 2 times 5. Any number which is not on this list is going to have some odd factors. So instead of proving that these can't be done, what I want to do is prove to you that whenever I add consecutive numbers, I'm always going to get a number from here, a number that's got odd factors, or at least one odd factor. Okay, so I'll just repeat that again. We think this is impossible to do, and I'm going to prove that by showing you that whenever I describe a number, whenever I can split a number into consecutive numbers, I'm always going to get a total which has got an odd factor. Okay, so here goes. Let's imagine that we've got consecutive numbers. And we're going to carry on. Yep. So I'm not going to decide how big my first number is at this stage. I'm not going to decide how many. So this could just be 5 or 6 consecutive numbers, but it could be 106 consecutive numbers. This could be a small number, or it could be in the thousands. Now what happens? How can I add these numbers? Well, one thing I can do is I can take this and turn it upside down, and like a jigsaw, fit it in. See if I can get these to be more or less. So that maybe these should be a bit longer. So this bit of the bar ends up here. That bit ends up there. That bit ends up there. This one ends up there. So this is quite a nice, clever way of adding lots of consecutive numbers. Because all I need to do now is work out the area of this rectangle. And then I need to halve it, because I only want half the area of the rectangle. So my yellow numbers make up half the rectangle. The whole rectangle gives me the sum of the yellow. Okay, so what could my first number have been? Well, let's imagine it was an even number. And let's imagine this was an even number. What does that tell me about how many rows I have? So numbers go even, odd, even, odd, even, odd, even, odd. And I'm finishing with even. Yeah. There's going to be an odd number of rows. If this is even, then this must be even. If this is even, then this must be even. So the width of the rectangle is even. I said I only wanted the area of half the rectangle. So I'm going to be able to split the rectangle in the middle. Once I've worked out the area of the rectangle, I can cut it in half. Half the rectangle is the sum of my consecutive numbers. But half my rectangle is the width times an odd number. So that total must have an odd factor. Okay? But what if we didn't start with an even number and finish with an even number? What if we started with even and finished odd? So if this is odd, this would have to be odd. Would this still be odd? So now, okay, we want to work out the area of half this rectangle. So this is even, so half the rectangle I can just imagine splitting this way this time. And I'm going to get the area of the top half. What can you tell me about the width of the top half? Even plus odd is going to be an odd width. So the area of the top rectangle will be a number which has got an odd factor. So perhaps we shouldn't start with even. That's where our mistake was. Perhaps, why don't we start with odd and finish with odd? Start with odd, finish with odd. What can you tell me about the width of that? Is it going to be even or odd? That's going to be even. Yes? Odd number plus odd number gives us an even total. What happens here? How many rows am I going to have? If I start odd, I go odd, even, odd, even, odd, even, odd, even, and an odd. So that's going to be odd. So now, the area of the whole rectangle can be halved by cutting it here. Half the area of the rectangle represents my number that I'm representing by my consecutive numbers, and this has gives me a rectangle with an odd height. So it must have an odd factor. So the only thing that we haven't tried is starting odd, finishing even. Odd, finishing even. If I start out, finish even. Odd plus even. So you can see what's going to happen. I can split the whole rectangle in half this way because I've got an even total, an even height. But the width of what's left is an odd number. And so it's going to have an odd factor. So whenever I add consecutive numbers, I always end up with a total that had at least one odd factor. That is why I can never end up with a number here from this collection. Okay. I partly wanted to show you this because we're so used to explaining things algebraically, and of course one could do this algebraically, but I think the diagrammatic proof is rather more beautiful than the algebraic one. And I suspect many of the adults in this room will have leapt to doing things algebraically, and perhaps just not known that there are things that we can work diagrammatically. Okay, I think this might be a good time to just stop for a minute or two. We've had some late arrivals, so it might be quite nice to be able to explain to them what we're doing. But I'm also quite curious to know what you've been discovering and finding out. So, first of all, just to explain what's on the board for the new arrivals, we've been trying to find ways of representing numbers as the sum of consecutive numbers. So 15 is rather special because it can be written as the sum of 2 consecutive numbers, it can be written as the sum of 3 consecutive numbers, it can be written as the sum of 5 consecutive numbers. And I'm curious about one of the things, whether you've noticed anything in general as you've been trying to find numbers that